كده بدأ. فين الصوت؟ طب مين شايف كده في صوت وصل ده؟
اشتغل من هنا كده احنا بدأنا التسجيل
يعني اسمه
الحصة بدأت.
Start. Yes. Can you hear me?
Yes.
Hello, assalamu alaikum. This is Ahmad with you. Today, inshallah, this lesson for third secondary, we will start chapter 7. Chapter 7 talks about laser, and we will start inshallah, talking about chapter 7, talking about laser. Previously, you have learned that the atom has two states. One state is the ground one, which the atom does not receive any form of energy. And the other one is the excited state, where the atom absorbs certain amount of energy, and this amount of energy will result in movement of some of its electrons from the ground state to a higher energy state. So, shall we start now talking about the first part? Let's start by the definition of lasing. Lasing comes from the word laser. Lasing is simply, it's a process of amplifying the light intensity by stimulated emission of radiation. If I have light, and this light has a certain intensity, and I would like to increase this intensity, I have many ways to do it, but laser is all about stimulation of the intensity of light. So I amplify. Amplify means to magnify or make it bigger. I amplify the light means I increase the intensity of light, and I do this by a process called stimulated emission. We will study everything about the stimulated emission later, but let's now talk about from where the word laser come from. The word laser actually came from an acronym, which is the start of or the beginning of letters from a statement or a phrase. I take the first letter of every word and I put them together to form laser. So if you look here, I have laser, L-A-S-E-R. L stands for light, A stands for amplification, S stands for stimulated, E stands for emission, and R stands for radiation. So if we put these letters beside each other, we will have light amplification by stimulated emission of radiation. So this is the meaning of laser, say, amplifying light by the stimulus emission of radiation. Now, let's talk about stimulation of the atom or excitation of the atom. The atom has two states. One of them is ground state, which is the normal state. And the other one is the excitation or the excited state of the atom. We'd like to know first how the atom got excited, or what is the reason behind the excitation of the atom. We know that the atom has a certain amount of energy, and that energy allows the atom to stay in one state. If the atom acquires or gains some energy in the form of heat or electricity or anything else, or even photoenergy, the electrons will jump from the ground state to a higher energy state. We call the atom, in this case, excited atom. So the excited atom is an atom that has some of its electrons already transferred from ground state or normal state to a higher energetic state. And we call now that the atom is excited, or the atom in excited state. As you see here, this level is the ground level, and this green ball represents the electrons. So jumping electrons from ground state to a higher energy state. This is now the expression of how the atom got excited. We said that the excitation of the atom could happen if the atom receives or acquires a certain amount of energy. Why the atom got excited? Simply because of the absorption of energy. The atom absorbed some kind of energy or some form of energy, and this energy allowed the atom to transfer from ground state into a higher energetic state. We call it excitation. But then what happens after exciting the atom? The atom got excited. It will never stay like this forever. A change must happen. When the atom got excited, as you see here from the diagram, here the atom in excited state, E1. E1 is the ground level state or the normal state. If the atom receives a certain amount of energy, now some of electrons will jump to a higher state. As you see here, the green ball is in E2, which is higher energetic state. We call it excited level. What happens is this electron will never be happy in the higher energetic state, so it will go down to the original ground state, E1, and the amount of energy that caused the electron to move in the first place will be released. Let me repeat this part again. When the atom got or absorbed some amount of energy, some electrons will jump from the ground state into a higher energetic state. Now, the electrons will never be happy in this excited state, and it will go back to the original ground state. But because it absorbed a certain amount of energy to transfer from E1 to E2, this amount of energy has to be given back as kind of energy. So here you have H nu represents the incident photon. Incident photon means it's a photon that carries energy. And the energy will be expressed in the form of H times nu, as you know that from previous lessons. H is Planck's constant, and nu is the frequency. So the incident photon represents energy, and this energy given to the atom in the ground state so that it will be excited to a higher energetic state. Once the atom will return to its ground state, or the electrons will go from the higher energetic state into a ground state, this absorbed amount of energy has to be given back. And the difference between E1 and E2 is delta E. So delta E is E2 minus E1. Okay, so here I put the statement here, and let me make it a little bit smaller. Okay, here you have the excited atom loses its absorbed energy and return back to ground state while emitting the energy it has absorbed in the form of photons, equal to the difference between the excited state. So the amount of energy released when the atom returns to its ground state is the same amount of energy absorbed in the first place. So that energy will be conserved. Now, let's go now to what happened. Here is a diagram that represents the action in details. Before the emission, what happens? You have the atom from ground state jump to a higher energetic state. So the atom in excited state because this level is the ground one and this level is the higher energetic level. And now we call the atom is excited. As we said that the atom will not be happy and will prefer to go back to its ground state. As you see here, the arrow goes from the higher energy state to a lower one. This is during the action, transfer of the atom from the higher energetic state into a lower energetic state. And as a result of this, a photon which carries energy equivalent or equal exactly to the energy absorbed to cause the transfer in the first place. So the photons will be released, and of course the photons will carry energy in the h nu. H is Planck's constant and nu is the frequency. So as you know here, the atom now in ground state. So the atom returns back to E1, which is the ground state. Okay, now emission is releasing photons of energy. Simply any kind of emission of radiation is releasing photons of energy. Whether this kind of release is spontaneous or stimulated, but in any emission we have photons of energy coming out. Now emissions are two types. We have two types of emissions. The first type is called spontaneous emission, and the second one is called stimulated emission. Again, emissions are two types, spontaneous and stimulated. And let's talk about, before we discuss each one of them, let's talk about what causes this difference between the two names. The difference between them is based on the timing of the return to the ground state after excitation. What does it mean? It means that the electrons, as we said, or the atom in general will go from higher energetic state to a lower energetic state by losing a certain amount of energy it absorbed in the first place. Now, the timing of returning the atom from the excited state into the ground state is all the difference between the two types of emission. What we mean by this is the time taken for the atom to return to its from the excited state into a ground state back again. It is a very, very short amount of time. It is 10 to the power of negative 8, 10 to the power of negative 8 seconds, which is less than a millionth of a second, less than even 1 million of a second. So despite that, this is considered, when we talk about small little things, it's considered a significant time. It's not something that we measure in everyday life. It's very, very small time, but it's enough to make the difference. We call this amount of time 10 to the power of negative 8 seconds. We call it lifetime. Lifetime. Okay, So if the return happens after a certain duration, which is 10 to the power of negative 8 seconds, emission is called spontaneous emission. Because why spontaneous? Because the atom actually takes this time to return without any external factor or any other stimuli to its ground state. So the atom, after excitation, returns back to its ground state with no other effect. Nothing affected it, nothing caused this kind of return back. And that's why we call it spontaneous, because nothing external affected it. So if the return happens before the lifetime, before 10 to the power of negative 8 seconds, we call it spontaneous because nothing affected it. But if the return happens before this amount of time, a lifetime, before the 10 to the power of negative 8 seconds, we call this stimulated emission. So the stimulated emission is return the atom from the excited state into a ground state before the lifetime, before it happens spontaneously, okay? And that caused the stimuli, that called the stimulus emission. Back again to this time, which is very, very important because it determines the difference between spontaneous emission and stimulated emission. It's called lifetime. Let's define the lifetime. Lifetime is the time duration for the excited atom to lose its excitation energy and return back to its normal state without external interference or stimulus. It's a return back without any external factor. That's the lifetime. And we mentioned earlier that this lifetime is very, very short. It's 10 to the power of negative 8 of a second. Okay, let's now define the spontaneous emission. The spontaneous emission is emission of radiation from the excited atom when it loses the energy it absorbed. And this happens after the lifetime. So it happens without any external factor. Let's now remind you of what's going on. This is the ground state, and this is the excited state of the atom. And here I have electrons in the higher energy state. Now it returns back to the same ground state, and it will release the energy it absorbed in the form of photons with energy h nu. Okay, so how about stimulated emission? In a stimulated emission, the story is a little bit different because the return of the atom from the excited state to the ground state takes place before the end of the lifetime, which is 10 to the power of negative 8. So it happens very, very fast. This return happens very fast. So the atom got excited from E1 to E2. And before it goes back to its ground state, another photon of energy h nu hits the atom, causing this atom to go back to its ground state, releasing the amount of energy equivalent to the amount of energy received in the first place. But this happens with something very significant. What is significant here is the energy of the coming photons is the same like the energy absorbed by the atom to jump from the ground state to a higher state. So I have here two rays of energy, and these two rays of energy, they are the same, exactly the same. They carry the same energy, they have the same frequency, they have the same direction, they are in phase, they are parallel to each other, they have the same intensity. Everything about them is the same, and that's because the energy of the coming photon is the same energy that the atom absorbed to be excited. So here I have two rays of energy coming out instead of one. But if you tell me now that E2 minus E1, the change of energy, delta E, equivalent to H nu. What's delta E? The difference between the energy of the ground state and the higher energetic state. This is delta E, which is E2 minus E1, equivalent to H nu, Planck's constant, multiplied by nu, the frequency of the energy absorbed by the atom. And if we look at the diagram here, you might think I have incident photon carrying energy, and at the end I have two. This violates the law of conservation of energy. If I have one, I must have one at the end. But if I have one in the beginning and I have two, this is a violation of the conservation law of energy. But if you look carefully at what has happened, it's not a violation of the conservation of energy. It's actually the opposite. Now, why is this? Look at this one. This energy of the photon comes from outside. The energy, the other type of energy, came from the return of the atom to the ground state. So, return to the ground state releases energy, and I have original energy coming to hit the atom. So I have two, one, and the other one comes from the return of the atom to the ground state. So it's not a violation of the law of conservation of energy, because one of the energy comes from the original part, and the second one is from the return of the atom from the excited state into the ground state. So it's not a violation of the law of conservation of energy at all. Let's now talk about the basic concepts in all kinds of emissions. In all kinds of emissions, we have specific things to look at, and if we know these things carefully, we can understand the theory of laser very well, and we can understand why laser is very, very unique and special form of light. And all the properties of laser can be understood by just paying attention to the basic concepts in all kinds of emissions. If I have any kind of emission, there are things I look at. Number one, the wavelength range, or sometimes we call it the bandwidth. What do we mean by this? The bandwidth, if you look here, this is a diagram to show me one color, monochromatic light. Say, for example, this is the yellow light. So the yellow light, look at this one and that one and that one. And so let's start now by the normal yellow light. You have the wavelength, this one, 580 nanometer. And this represents the yellow. But as you see, the bandwidth, which is the distance from here to here, it's actually wide. It ranges between 555 nanometer into 595 nanometer. So we have wide range of the same color, and before it you have green, and after it you have orange. But yellow color has a band width which is a little bit higher or bigger, and this means that I have many shades of the same color. So the yellow color has many shades, varies between like dark yellow or light yellow and so on. And So the band here, the yellow band in the middle is ranges between it's a little bit closer to 580 as you see here. So the bandwidth of this color is a little bit smaller than this one, which means that the yellow color is getting a little bit closer to its value, and the bandwidth is now 20 nanometer. And here you have what we say it is monochromatic, which means that the bandwidth became very, very small, and that makes the color sharper and clearer. So as you see here, the big or the wide range of bandwidth causes this yellow color to have many shades, and as the bandwidth getting smaller, the yellow color becomes monochromatic. Monochromatic means that the light is sharp and does not have many shades. The second property we talk about is the wave phase or coherence. If you look at this wave and the one under it and the one under it and the one here, you have 1, 2, 3, 4. You have 4 waves, and these 4 waves are coherent with each other because the coherent light waves, they have the same phase with each other. The same phase, why they have the same phase? If you look here, this one starts to go down, the other one goes down. This one also goes down, goes down. When this one is getting higher to this point, the maximum, the other one underneath it goes also to the same point. So they go with each other, which means that they are in phase. They are in phase, the same place at the same time. We call this kind of expression when waves, they go to the same place in each time, we call it coherent light waves. So the coherent light waves are waves which are moving and having the same place at the same time, so they are coherent. They have the same phase. The third factor we talk about in laser is the intensity of wave beam. The intensity of wave beam and the obedience of the inverse square law. One here diagram talks about how the distance affects the intensity of any kind of light, including the laser. If you have the source, and this is the source of light, imagine now this is the normal light. As we go far away from the light, the distance increases. So the relationship between the intensity of light and the intensity of light and the distance away from the source is inversely proportional to the square of the distance, not to the distance. As you see here, the intensity E divided by, say, 1 meter. So here, not 1 meter, it's 1 meter squared. 2, you have 2 meters squared. When I move a little bit, 1 meter more, it's E divided by 3 10 to the power of 3. So this means that it is not inversely proportional to the distance, it is inversely proportional to the square of the distance. So the further away we go from the source, the less intense the laser will be. So factor number 4 is called the collimation or dispersion of the wave beam. The collimation or dispersion of the wave beam, I mean simply by this how the laser will be dispersed or how the laser goes scattered as a form of the rays they got dispersed or away from each other. So as you see here, this is the form of source of laser and the beam is coming out. As you see here, the beam is not scattered. Scattered means the diameter at the start is the same like here, the same like here, the same at the end. So this means that it's not getting wider, it's not getting scattered or dispersed as we go away from the source. So as we go away from the source, not dispersed. As we go here, let's talk a little bit about the difference between the monochromaticity, coherence, and collimation. After understanding that the intensity of light depends on the distance between the source and where we are from the source, and we said that it's inversely proportional to the square of the distance, let's talk about the three things that might be a little bit confusing with each other. Like they might confuse you because they are a little bit related, but not they are not exactly the same. So I would like to compare them with each other. These three concepts they are called monochromaticity, and the other one is called coherence, and number three, collimation. So I have monochromaticity, coherence, and collimation. Let's talk in the beginning about the first one that we discussed. The first one is the coherence and collimated. The wave can be coherent, but at the same time not collimated, as you see here. I put the waves in two forms. One of them is horizontal and the other one is vertical, to just check how they look like. Coherent and not collimated. Look at these waves. They are coherent. Coherent means they go with each other in phase. This one starts here, it goes down. This one starts here, it goes down. This one starts here, goes down. And then rises up. Also rises up. Also rises up. So they are coherent. They have the same phase. But actually they are not collimated. Collimated means they are not parallel. If you look here at the direction of propagation, this one, and the other one, they are not actually parallel. The direction of propagation of waves are not parallel, or we have name for this, they are not collimated. So they are not collimated, and if I change the propagation direction of the waves to upward, I find that it's easier even to look at it like this. They are not parallel with each other. They are coherent. They are in phase, but they are not actually having the same direction. Another point of confusion is the relationship between, as we talked about, coherence and collimated waves. If you look at it, it's I put the waves here in the form of vertical and horizontal. This one is incoherent, and this one is incoherent with this one. This one is incoherent, and this one is incoherent, but they are both of them collimated. What do you mean by this? They are parallel. This wave parallel to that wave, parallel to that wave. They are parallel in the direction of propagation. So they are parallel in the direction of propagation, but they are incoherent with each other. Incoherent means they are not in phase. Look at this one. This one is at its bottom, and this one is not. This one has its bottom, this one is not, and this one is not. So they are not in phase. In phase means to compare a point here and a point here and a point here to see if they are at the same place at the same time or not. So they are not in phase, which means that they are incoherent. Now, they are collimated. Collimated means they have the same direction. So they are incoherent, but actually they are collimated. So being coherent and collimated, they are not related with each other. They can be one or the other. One other point of confusion is that can the wave be collimated but not